Thanks. Hi, I'm Axel. I'm from Paderborn University. I'll talk about class expression learning with multiple representations. And fundamentally, we'll go back to the CRISP world, but a lot of the things I'm going to talk about, you can actually think or try to extend really cognitively to the non-CRISP world. It just makes my life easier to talk about those concepts within that particular space. Without any further ado, why is this interesting for this particular summer school? Imagine that you have a cooking robot, for example. That cooking robot is thrown into a new kitchen. The cookware is unknown, basically pots, knives, and so on. So it basically has to think, okay, I'm not giving all of this, and I'm giving a recipe, for example, make an apple crumble. And my fundamental question is, which utensil should I then use to, for example, perform one of the tasks in the recipe, which is I need to basically chop apples. It's not only that I want to be able to pick the right utensil, I also need to be able to say why I picked that particular utensil. If you think about collaborative settings where the robot and a human, for example, are then to be cooking together, the human might have questions as to why the robot actually performed a certain action in a certain way with, for example, a particular utensil. So fundamentally, what we're interested in this area of class expression learning is basically learn based on previous experiences or learn based on external knowledge sources in such a manner that we can actually explain the classes, so basically the classifiers which we learn. So really that is fundamentally what class expression learning is all about. So for example, we might want to learn that if I want to use something use something as a chopping device, it has to be something that has a blade length of 15, 16, or 17 centimeters as basically an example. Those would be your prototypical blade lengths for knives. Now, the main advantage of doing class expression learning, I'll define that formally in a second, is obviously that it is explainable because whatever we learn here, the expressions that we learn, we can actually verbalize, turn into natural language, and present to people who have absolutely no idea of description logics, and they're still able to understand why we perform certain actions. The main contra of class expression learning, at least the way it was done classically, is that it's slow. So basically, it does not scale to really large knowledge graphs or knowledge bases. And fundamentally, what I'm going to talk about are means to make things faster so that we can actually get to apply this type of learning to larger knowledge graphs, really. So, but before we do that, and to motivate why we're going to use multiple representations, let's play a little game. So the idea of the game is relatively straightforward. Your job is to answer my questions as quickly as you can. So basically, I will read the questions. Feel free to answer even before I'm done reading, okay? Are we all ready to go? Yes? Are we sure? Good. All right, number one. What's 3 plus 3?
6.
Good. What's the square root of 4? What's the capital of France? Okay, now close your eyes for the last question. I'm not going to steal your stuff. So, think of an apple. Which color does it have?
Red.
So, who says red? Who says green? So it's roughly 50-50. If you prototypically ask that question in Germany, you get a distribution commonly of somewhere between 20% for green and 80% really for red, because typically in a supermarket, what you find is red apples. I checked in my supermarket, there's few supermarkets around and asked around as well. That's roughly the kind of distribution you expect. But what is interesting here is that if you look at the Son of Man, this particular picture, long enough, because there's a green apple there, your brain can actually be primed to see apples green suddenly instead of red. Now, this is a phenomenon which has been studied. There are plenty of books on the subject matter. I think Kahneman is kind of the most commonly known book in the literature here, which basically talks about system 1 and system 2. System 1 being responsible for intuitive responses, being time efficient, but basically carrying out a lot of the cognition or the processing in an unconscious manner, simply based on what is assumed to be a lazy representation of the problem. While system 2 is in charge of our logical responses, where we do explicit computation, but it is resource intensive and is based basically on an explicit representation of the data that is necessary to process the question at hand. And it turns out that humans actually are, okay, both systems are trainable and configurable, but interestingly, humans tend to use or seem to use multiple representations to actually solve problems and tasks. And that was actually the reason why we thought about and we started pondering, can we use multiple representations for structural machine learning, really for class expression learning, and how beneficial would that be to said problem? So we basically did nothing else than taking the problem apart, saying what are the main components, and do we actually need to use the same representations when we're trying to tackle these different subproblems? It turns out really we don't, and it does help to use several representations. So basically that's what this is all going to be about. But let's define what we're dealing with formally first. Class expression learning belongs to the family of supervised learning problems. Supervised learning problems basically tells you we are going to have positive and negative examples, or at least positive examples to what we're dealing with. And class expression learning deals with background knowledge. So we basically do supervised learning with background knowledge. And the definitions I'm going to bring about here are adapted from previous works by Lehman and Hitzler. So we assume that we're given a particular formal logic. That could be ALC, which I'm going to show you in a sec. Who's never heard of ALC actually in this room? Oh, cool. So most are familiar with so I can rush a bit over through that. Good. We have background knowledge in the form of a knowledge base with a particular T box and a particular A box. And we're giving a set of positive examples, which belongs to which is a subset of the named individuals, and a set of negative examples as well. The problem which we're trying to solve is to find, you'll find that in the literature there are several formulations of the class expression learning problem. We're going to be working with this one, where we are to find at least one hypothesis H, which belongs to a set of hypotheses, such that, number one, H is a class expression in L, so in the formal logic that was given to us. And ideally, this ideally is actually quite important because in most cases, finding exactly an ideal solution is difficult, if not impossible. But ideally, what we want is that for all positive examples, we can really have that K subsumes of that we can really infer H of E plus from K. And for the negative examples, it should be such that basically H of E minus does not belong or cannot be entailed from K. So basically, we want to find a class expression which describes the positive examples and does not describe the negative examples. That's fundamentally what we're after. In general, we'll find that it is difficult to find exactly that, so we'll have to find a measure of the goodness of a class expression, and we're going to try to find a class expression which is as good as possible with respect to the problem which we have. And this is really a sketch of how most class expression learning systems work. So obviously, I just described that we have some form of training data, that's E plus and E minus, right? We are given a knowledge base, and we typically start with a candidate solution. Now, depending on the type of solution or algorithm you're dealing with, this might differ. If you're thinking about top-down refinement operator, which I'll describe in a second, really this candidate solution at the beginning is commonly the top concept, which basically describes everything. The top concept or candidate solution is then combined with the training data via a quality function, and the quality function is really just there to tell us this is how good this particular solution is with respect to the problem at hand. This quality function depends on a commonly rather costly retrieval function. And the job of the retrieval function is really giving our class expression to say which are the individuals which are such that their interpretation actually belongs to the interpretation of the class at hand in a model of our knowledge base. So this is usually where we spend a lot of time computing, right? So fundamentally what we're saying is how much of E plus does H describe? That's what the retrieval function will do for us here. And based on the quality function, applied to our candidate solution using our retrieval function, we now know really how good we are, and we can then use this information for the next step, which is going to be candidate generation. So we have a candidate solution, we check how good our candidate solution is or candidate solutions are, and based on that we select most commonly a candidate solution, apply an operator to it to modify it. So basically we start searching in the space of solutions, and we apply that operator iteratively until we get to something that we deem good enough to terminate, or until we've basically used up all the resources which we had. Okay, so example of that. So one formal logic which is very commonly used and considered in this particular setting is ALC, attributive logic with complement. So what the type of constructs which we have are the following. We have top, which basically describes everything. We have bottom, which describes nothing. Then if we have C and D to be ALC concepts, and if R is a named role, then basically, obviously, C, which belongs to NC, is going to be an ALC concept. We have negation, intersection, union, and we have these two constructs. Exists RC, which basically means something which is connected via R to an instance of C, or for all RC, everything connected with this particular thing via R must be an instance of C. So if we remove the negation here, as well as the union and for all RC, we are basically looking at EL, which is a different description logic. A lot of my examples are going to be based on ALC or EL, just FYI. So this is the type of formal logic that we can be dealing with here. I told you that we commonly use what we call a refinement operator to generate candidate solutions. What is that exactly? So if you assume that you're in a particular space S, so basically a set, for example, of all concepts with a particular quasi-ordering, so basically, or partial ordering really, something like subsumption, then a top-down refinement operator, obviously bottom-up will be defined exactly the other way around, will be a mapping from S to the power set of S, which is such that it ensures that rho of X is subsumed by X. Okay, so basically, whatever is an element of rho of X must be a subconcept of X itself. So this is basically what such a refinement operator could look like. Don't worry too much about the details. Fundamentally, once you have the slides, you can try to check whether the condition which I stated up here really is fulfilled. But for all intents and purposes, you can basically see that what this operator would do is, if we are dealing, this is top, exactly. If we're dealing with top, so we start at top, it will first start by generating all elements of NC as well as all exist RC kinds of constructs. And then it will, if it is asked to refine one of those elements, for example, an element of NC, is going to try to add further constructs or basically go down the class hierarchy so as basically to find a solution which is subsumed by the solution already available. And that way it would aim to traverse the search space for concepts. Okay, so what would that look like if we were to do class expression learning with this particular example? Our positive examples here are Louvre. Le Louvre is here, and Tour Eiffel here. And our negative examples here are Lily and James. So what would a prototypical class expression learning algorithm do, assuming that we're dealing with ALC as our description logic here? We'll obviously start with top and basically say, all right, I have Louvre is obviously an instance of top. The same holds for Tour Eiffel and for Lily and James. So 50-50, not that great a solution. Let's try to refine that. I would then look at, for example, all the instances of NC. And you can look here and see, well, Louvre is defined as a museum, while Tour Eiffel doesn't really have any class expression. So it basically be connected directly to top. That is obviously not the greatest class expression. And we'll basically keep on iterating and saying, can I make things better? And an algorithm will basically land somewhere here. Half the hypothesis exists, is located in place. So if you look at Louvre and Tour Eiffel, they are both located to something which is of type place, and that obviously does not describe Lily and James. They're humans. There's no location information here. Obviously, it already tells you we're dealing with closed world reasoning here. Okay, what you would not learn, which would be an expression which most humans would probably prefer, is something like those are buildings located in Paris, simply because we cannot express classes which are basically made up of single elements, right? So fundamentally, that's what we're trying to get at. I hope that the problem we're dealing with here is now clear. Question is, can we make these different functions, so these three functions, better by looking at other representations of the problem than the standard representations which we normally use? So what I'm going to talk about is the fact that retrieval is expensive, but that we can actually solve that problem by representing concepts in a different language, which is Sparkle, and then representing a knowledge graph as a tensor, and really using tensor operations on that tensor representation to improve the speed of actually the retrieval function. Second problem we're going to deal with is the fact that quality functions are often myopic. The way they are described is such that they actually do not look into the future. We will try to define, or we will define, non-myopic quality functions and actually use that to improve the runtime of class expression learning. Candidate generation is expensive. We will represent individuals really as graphs and use those graphs for priming our solution. And with priming, we'll basically be able to run faster. And the search space being large means we need a way to do pruning, and basically by representing concepts as embeddings, we can actually prune the search space in an efficient manner. Now, this is a lot of material. I'm not going to try to cover all the details thereof. I just want to give you an impression of what one can do here, but I'll be more than happy to answer questions pertaining to details if you happen to have some. So let's delve right in. Representing concepts as Sparkle. So if you assume a closed world, that is fundamentally an assumption we kind of have to make here, and a fully materialized knowledge graphs, Bin et al. Have already shown that really retrieval in ALC can be performed by representing concepts as Sparkle queries. So this is a known and established result. The idea here is that they define a recursive approach to building the corresponding graph patterns. And basically this P here is the graph pattern for a particular class expression Ci with respect to a particular variable var, right? So that's fundamentally the graph pattern that we want to find. If A belongs to NC, all we really need as a Sparkle query is to compute var where RDF type is A. And we can actually make use of all the work in indexing, which has been carried out in the area of knowledge graph storage, to compute this faster than you would do if you were using a normal retrieval function from a reasoner. The result sets, however, are equivalent with respect to transformations. So if you want to have not C, what we need is the following Sparkle query. So basically, we will carry out a filter not exist on tau of C with respect to var and have var PO union SP var. Pretty straightforward. Now, when it comes to intersections, well, that's also pretty straightforward. Those are conjunctions in Sparkle. So we can, if you have intersection of C1 to Cn, all we need to compute is tau of C on var and C2 var and so on and so forth, up to Cn var. That's pretty straightforward, pretty obvious. The same holds for unions. Exists RC, well, all we really need to do is have var Rs and tau Cs. So basically find all the vars which are such that there's at least one S of type C connected with them. For all RCs, slightly more tricky because we basically want all the things connected via R to var to be of type C. But it turns out that we can do that simply via counting. So all we really need to do here is to take a variable, check for all the things connected with it, count how many things are connected with how many distinct things, and then do the same for the distinct things of type C, and simply check whether those two numbers are the same. And if they're the same, then we have really an instance of this particular class or class expression. Okay, so fundamentally, what this particular result tells us is that by looking at the retrieval problem as a Sparkle query execution problem, we can actually improve runtimes. And that paper already showed that by using standard Sparkle machinery, one could do that. But it turns out that by looking at the problem from a perspective of tensors, we can do that even faster. And this has to do with the fact that really fundamentally, a lot of the works on storage solutions for knowledge graphs are based on ideas from the database area, where one has some form of a resource index, of course, one needs that, and one has a triple index, but a triple index is commonly something like a B+3. A B+3 is a good data structure, but when one knows that one is dealing with triples, ergo the order of the type of tables, quote unquote, that one has to deal with, one can actually perform better here by representing the whole thing as operations on order 3 tensors. So this is an idea from Beagle et al. 2020, but there have been previous works on basically tensor representations for storage. The fundamental problem that was found in these papers so far is that property-property joins were not possible, but the inherent representation that was used was really an extension of matrices for the computation. But if the idea in this work is that we can exploit tensor representations to accelerate querying, the key here is to devise a data structure to accommodate this rapid querying and obviously to transform these Sparkle operations into tensor operations. So how does that work? Imagine that we have this particular knowledge graph. So we have a bunch of entities, E1, 2, E4. Two of these entities are unicorns, and the relation that we have, relations which we have are both knows. So basically, for example, E1 knows E2, and the type relation which basically tells us that E2 is a unicorn. So this we can obviously transform. Number one, we need some form of index structure, that's standard part. We can give these things an ID, very straightforward, 1 to 8. The key here is that number 8, and that is the key formally here, is that we always have an ID for the unbound things. And unbound things will later need to actually map variables. If we have this index table, then this graph is nothing else than this particular table, right? Order 3, and we have, for example, 1, 2, 3 in here, which basically means that E1 knows E2. Well, that's nothing else than a binary tensor, a very sparse binary tensor of order 3. So, I'm not going to spend too much time on this, but fundamentally it means that as a data structure, we need a data structure which can represent data or knowledge graphs in the following way. We'll basically consider order n tensors T to be mappings from an n-dimensional key space to some form of a codomain. And the codomain that we're going to be interested in is obviously the binary codomain if we are not considering counts, or the natural numbers if we're considering counts. And we're currently looking into actually looking at the real numbers here. That would basically cater for dealing with probabilities. So, whatever, all elements of K will be called keys, and these keys will have parts, K1 to Kn. For all intents and purposes, n is going to be equal to 3. And we can access such a tensor simply in array style. So when I write T of K this way, I basically mean the entry at position K within the tensor. So in this example, K is n to the 3, V is the Boolean space, and T of 367, because it is found in our tensor somewhere, 367 is there, will be equal to 1, while T of 363 will be equal to 0. Okay. On this tensor defined this way, we can define a slicing operator. And what slicing does is really to select portions of T. So if I write T1 column, so the slicing operator is basically denoted using a column, what I really mean is an order 1 tensor where where the first and second entry with respect to the original tensor are bound to the entries which you find at 1 and 2. So basically, I'm defining a vector here. So in our example, T12 will be 0, 0, 1, 1, 0, 0, 0, 0. Because those are basically the values that you find for 1, 2, 3, up to 8 within the tensor. Okay. Now, once I have represented things this way, I can actually define a join on a tensor. And I can define a join in a tensor really simply by implementing Einstein summation. That's really the key here with respect to rapid computation. Everything is an Einstein summation. So if I take this example, for example, of select F, where E1 knows F, F knows U, and U is of type unicorn. So I'm basically asking for, basically for people who know unicorns. I can take each of these triple patterns and actually map them to a slice of my tensor. Pretty straightforward so far. But then, because I have the join operations, my join operations are really just Einstein summations with respect to the running variables, which are basically carry out the join. So the answer, which I'll expect here, will be nothing else than T1 to column with respect to running variable F times T. Here we have here a column and there a column because those are variables. So column to column. And obviously the ordering of the variables is important. So respect to F and U times T column 6, 7 with respect to U. So all I really need to do is run this as each entry of my vector will basically sum over the multiplications of these tensors. And I have a join. Cool thing, this is basically a binary. It can be executed even in parallel very, very efficiently. So it basically means that I can now implement some of the key operations which I have in tensors, basically actually in the Sparkle algebra, within this particular formalism. So a triple pattern is really nothing else than looking at the key values. Pretty straightforward. BGPs, I really just showed you, so basic graph patterns with joins. All I really need to know is where am I running variables, and a basic graph pattern is nothing else than actually running an Einstein summation with respect to the ordering of these running variables. And a projection is really the same as a BGP, except for the fact that I will omit some of the results, right? I'll simply take the portion of the results which I am interested in with respect to the variables which are to be found in the projection. So, what have we done so far? We've really taken class expressions and we've mapped them to operations on tensors. What we really need is a data structure which caters for these operations. And it turns out that the hypertri data structure actually does exactly that. The hypertri data structure really comes from tries in computer science. The idea is really that if we think about representing this as a trie, we really have the problem that we can traverse a trie in exactly one ordering, subject, predicate, object, or predicate, subject, object, and so on and so forth. And if you think about the number of these data structures which we will need to actually represent all the data in such a tensor efficiently, we'll basically need 15 of those tries. And these 15 tries are obviously, from a point of view of memory footprint, but also from the point of view of joint ordering, a pain. And it's something that we're trying to avoid. So what the hypertri does, it allows to traverse a tensor in any order wanted. Fundamentally, the idea here is that we represent a tensor as via its slices. So the root node here will represent column, 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 right? It will basically tell you you can enter this tensor in any direction you want. It will tell you that in the first column, you can put the values 1 through 3, 4, and 5, and that works. In the second column, you can put 2 and 6. In the third column, you can put 3, 4, 5, 7. So basically, I have entries for these particular sparse bits in the tensor. And once you follow one of these arcs, say 3 here, you'll basically see that there's a first column here and a second column here, and these are the possible values for that. In this way, we have a trie-like structure, but a trie-like structure which we can traverse in any order of dimension we want. And it turns out that this way we can actually save 1/3 of the necessary memory footprint, while still catering for all the possible traversals here. Okay, how do we benchmark that? One thing that is rather important to me is that we do benchmarks in a clean way, in a repeatable way. And I think that's also going to be an important part of the collaboration here with Bremen, actually thinking about how do we benchmark properly. Here we used a benchmarking framework which is called Iguana. Iguana really allows to plug in a bunch of triple stores run queries and ensure that the queries are executed in exactly the same way, that the way the results are evaluated is exactly the same, so that a posteriori one gets comparable results. So we basically compared this data structure with the data structures used in vitro of 7.2, Fuzzy-Clip-Race graph, and GraphDB, which are kind of the most commonly used triple stores here. Timeout set to 180 seconds and a benchmark runtime of 60 minutes. We're not going to waste too much time on the details here. What's important is really this picture, number one, that even on small data sets, using this idea of using hypertries and traversing hypertries already leads to quite the significant gain with respect to runtime. And if we do that with larger data sets and we actually look at the speed up, this data structure has the main advantage that it speeds up quite quasi-linearly with respect to the number of clients which send queries, whilst most of the existing data structures actually either have a lower factor or actually crash on larger data sets when queried with a large number of clients. Cool. So, retrieval is expensive. How do we address that? We change the representation. We take the representation which we normally have, pack that into binary tensors, rethink really our operations to be operations on tensor representations, and with that we can actually improve the time or reduce significantly the time that we spend on retrieval. Clear so far? Cool. Then let's move on. Quality functions are often myopic. That's basically the second problem which we want to tackle here. How do we deal with that? What do I mean by that? So most commonly, as a reminder, what we really do when we're doing class expression learning is doing what falls under informed search in the space S of all concepts with a particular partial ordering. And we define a refinement operator and say, okay, our refinement operator is going to inform the way in which we traverse the solution space. So this is the kind of trees that we'll commonly go through. So if you imagine that you're dealing, say, with the university ontology, you will start with your top operator, then say, okay, there are person, places, and organizations. How good is that? A quality function will say, well, person looks good, and we'll say, okay, then let's refine person and look at that. We have basically perks, person works in as the, in this case, only possible refinement. Our quality function will say, top, please do continue, and we'll refine further until we get to a class expression which has a high enough F measure or whatever measure we're using, or which basically reaches one, then we terminate, we say, okay, we found a perfect hypothesis. Okay, so the fundamental problem with doing things this way is really that when we are at person, we really don't think about the children of person. We really think about, hey, how good is person? And we know, imagine that you're playing a game of chess, for example, and the only thing you think about when you play a move is the position after that move. You'll most likely lose. Most people do compute a few steps ahead and basically say, okay, what does the future look like based on this position? And I want a position where my possible futures actually look good for me, right? That's fundamentally what we want to do here. So technically, just to give you an overview, these are the kinds of functions which are used in the state of the art when it comes to actually evaluating the quality of a particular class expression in the search tree. So the OCEL algorithm, for example, works as follows. It will basically say, or the quality function thereof, it will say let RC be the set of instances of C. So R basically here stands for retrieval, and let C prime be the parent concept of C in the search tree. So we can imagine this to be C, and in that case, this would be C prime, right? So the concept I'm coming from. Two measures are then combined. One is some form of accuracy, which basically tells us how good this particular concept is. And the second thing that we'll add there is an accuracy gain. It basically tells us it's something like the gradient. I mean, obviously it's not the gradient, but it's supposed to emulate the gradient and say how steep is our winning curve here? How fast are we going towards this, the best possible solution? And by combining these two, the measure then tells us, okay, this is the concept that we should refine or not refine. And the accuracy here is defined as y minus magnitude of E plus minus RC plus RC intersection with E minus. So basically it tells us how much of E plus did we find and how much of E minus do we still have in our solution divided by the size of E. So basically just to normalize, while the accuracy gain is basically nothing else than the current accuracy, so the accuracy of C minus the accuracy of C prime. Current accuracy minus the accuracy we already had when we were at C prime. So basically what's our gradient. And then we can combine the two. What OCEL does is basically simply a weighted combination, and we basically also remove a little bit pertaining to the size of C, so we want short solutions. That's really for explainability. We want a solution that's short, that leads to a high accuracy gain, and which is accurate in and of itself. If you think about this measure, and you think about the tree we had, fundamentally what we're saying is let's look at the past, see how we got here, but we never think about where we're going, right? So we never think about what can the future look like with respect to this particular class expression. And it's basically very similar. Silhouette does something similar. Let's not bother about the equations. The important bit here is that this scoring function down here, the accuracy and accuracy gain are defined, or accuracy especially is defined differently, and hence accuracy gain, but still the fundamental idea remains the same. And it's basically what you'll find in most of the literature. So we are not interested in the future accuracies of concepts, which basically means from a perspective of reinforcement learning, that we are really working with gamma equals 0. And that's something we obviously do not want to do if we're doing something like a planning task. So our discounting factor. So the question was, can we do better by actually using cumulated future rewards? The scenario that we use is the classical reinforcement learning scenario, nothing particularly fancy here. So our state is simply the concept in which we are. Our reward at t is 1 if the accuracy is 1, 0 else. You'll find that in some implementations is basically something like a proxy for the current reward, and something like the Silhouette or OCEL score will be used here. And what we really need as transitions is the transition from a concept C to some concept D, right? So basically it's one step within our refinement tree. And what we want to do here is, instead of using a standard quality function, to use a proxy for a quality function, which actually considers future rewards. The important equation here is this one. So basically what we want to do, the way we want to do that is by minimizing square loss. That's pretty obvious. So what we do is we want to learn a Q function approximator, which is such that we actually know the real value of Q. We have a Q function approximator, which basically computes an approximate, therefore, and we minimize the square loss so as to have a good approximation of the Q value on our training examples, and we then use that particular Q function approximator as our quality function for later, for basically online training or online use of the algorithm. The way we did this is really by using a convolutional deep Q network with 3 parameters. The important bit here is that we basically did nothing else than embeddings for the E plus and E minus, so basically for the set of positive and negative examples. We then run a convolution on top, and really only 2 fully connected layers, and we can use this actually as a function approximator for the quality function instead of using accuracy and accuracy gain as done in the past. Now the question which I would have expected is, but how do you then embed this, guys? Who is familiar with knowledge graph embeddings? Who's never worked with knowledge graph embeddings? Okay, cool. That's going to be a run. Fundamentally, knowledge graph embeddings are actually pretty straightforward from the point of view of the fundamental concept. We basically say, well, we have a knowledge graph, that's a discrete structure. We want a continuous representation of this discrete structure. And the way we do that is, for example, by saying, if you had a trans-C algorithm, well, S, P, and O, so basically the head, the relation, and the tail are vectors. And we really want S plus P to be equal to O. Right? So we want to find vectors, a vector representation for S, P, and O that is such that that S plus P lands exactly on O. That basically will never happen if you have enough data and a small number of dimensions. So we basically try to find a good enough approximation. Now, the problem with this definition is that obviously it's trivial to find a solution which works perfectly, and it's to put everything to 0. So we also use negative sampling to basically ensure that that particular family of solutions simply does not work. So that was kind of really one of the first embedding algorithms out there. What you'll commonly find are more things like, let me just skip this for the sake of time. You're basically more going to find things like this these days. So what has been looked into is S plus P equals O. That's commonly in the real space. It does not cater for rotations. It does not cater for commutativity and so on, different characteristics really that relations can have. And what is often done now is basically embedding into hypercomplex spaces. Main advantage being that one can actually model characteristics of properties such as symmetry, asymmetry, commutativity, and so on and so forth. That is all possible if one caters for not only translations, but rotations and other operations in spaces. The approaches which work the best at the moment live in quaternion or octonion spaces, but there are also approaches which go further. There are some papers on how to use sedenions, for example, for this particular intent and purpose. Fundamentally, what we're doing is we're taking our discrete structure, we're mapping that to a vector space, and we can now use these vectors or these vector representations as features for a deep neural network. Hence, again, we've bridged across representations to be able to actually compute these quality functions and use basically all these Q functions, and we can use these Q functions really to improve the transition within our search space. And training data, and that's the cool thing here, generating training data is a breeze because we can really generate any concept we want, apply the retrieval function, know which elements are instances of that concept and which elements are not. Generate as much data as we want and train our Q function. So basically training data comes at no cost except for the computational cost for computing Q. And it turns out that with that, we're not only faster, we are basically better with respect to, I mean, this is just a sample of the types of results you get, but we really converge towards good solutions that are better than the solutions that are able to state of the art in a significantly better runtime. Okay, how much time do I have left? I guess like 5 minutes or something. I'm sorry?
15, but you can...
I have 15 minutes left? Yes.
If you're done,
No, I am not. So, candidate generation. Let me see. Do I have 15 minutes? I'm not sure of your answer. Okay, good. Okay, cool. So we've looked at retrieval, and we said it's expensive, changed representation, moved to tensors, and basically use tensor operations. We looked at the quality functions. We said they're often myopic. Well, change representation, look at it as a continuous problem, and solve it by doing Q-learning. Now, candidate generation is also expensive in the sense of if you think about our tree again, starting at top is kind of a suboptimal idea. What we really want to do is start somewhere which is likely to already be a good candidate and basically prune the top of that search space and then simply look below that. And it turns out that we can reuse this idea of priming by basically finding subgraphs in the graph based on our training examples which are likely to be good candidates. So this is work that was done by Hindorf et al., presented, I think, 2021. And the fundamental idea of this evil learner algorithm is let's go away from refinement operators, use genetic programming, but basically prime the population generation by using candidates from E+. So the idea here is we want to represent concepts as trees. For example, a concept like female or parent and married to male would be represented this way. And we want then to learn our class expressions in an evolutionary fashion by using basically the priming effect, ergo the idea of pushing our algorithm in a certain direction from the beginning. And the intuition here is that really an individual, if you think about it, is an overlap of several concepts. So by looking at a portion of the concise bounded description of our individuals, we can actually find concepts which are potentially good candidates for a solution. So the way the algorithm works is actually pretty straightforward. We start by selecting a positive example, say for example, person 1 here, add type information to the example, and actually just traverse the tree up to a certain depth as preset by the algorithm. So for example, here we could find the concept male and is married to somebody and has child. If we generate enough of these concepts based on the positive examples, we can actually prime ergo start our population that way. Instead of using the standard, let's begin with the random population. And then apply the classical operators, which we all know from genetic programming, to basically take those trees and refine them further. One thing which this algorithm does well, which most algorithms do not do, is actually considering data types, or really the D part of stroke D, if you're thinking about OWL1. And what it does is it reuses an idea from decision trees to basically split the values of the data fields in such a way that they have a low mix ratio. Different ways of doing that. What is commonly used is information gain, which is also used in this algorithm, but you can use entropy, Gini index, whatever. It all basically boils down to the same. In this way, again, we take a continuous problem in this case, and we can discretize the problem by simply having boxes where we have values within a certain interval. As I mentioned, training is pretty straightforward. We initialize, not really. Classically, one would do that randomly, but what we do here is really we take these candidates which we've generated from the positive examples, and then we run selection, crossover, and mutation exactly on this population. How does this perform? Well, it turns out it performs rather well on most data sets. So even on rather difficult data sets like hepatitis, the results actually are significantly better than what was available so far. The major problem here, obviously, is that this algorithm is non-deterministic. So if you look at the standard deviation here, it's actually pretty high, especially when you're dealing with complex problems. So one interesting research direction, obviously, here is, can we have a deterministic version of this algorithm that would make our lives significantly easier? What is also quite interesting is that data properties, in a lot of cases, not in all cases, play a central role. So the fact that the algorithm can actually discretize values, so change really this representation from a continuous to a discrete representation, actually really does help to gain quite a bit of F measures. So basically going from something like 0.44 to 1. There are a few use cases, though, where that actually leads to smaller F measures, but that is rarely ever the case. Okay, so candidate generation is expensive. It's actually relatively straightforward to solve. We can simply use priming. That's one way of doing it. Another way of solving or attacking this problem is actually by thinking about the search space and saying we are going to prune the search space not by saying where we cannot start or basically changing our starting point, but rather by saying we are going to not explore portions of the space. Given that I have very limited time left, and I would love to have a few questions, I'm going to rush through this one. It's going to be a quick one. So the search space is large. What's a good way to prune? Well, it turns out, and that really was to our surprise, that there is an easy way to prune such a search space, and it's really by limiting the length of the concepts. So basically what we can do is, again, move to the continuous space, move to the embedding space, and by looking at the data distribution, really ask the question, given this set of positive and negative examples, how long should the concept be which I learn? If I can do that, then obviously in my search tree, once I get to a certain concept length, I can say do not explore any further and simply look at other solutions because my prediction is the maximal concept length here should be something like 7. And that's really what the CLIP algorithm does. Fundamentally, we can define concept lengths in ALC, for example, by saying that the length of atomic concepts is 1, If we add negation, we add 1 to the length. If we add exist RC, or for all RC we add 2 to the length. And the length of C union D on length of C intersection D is 1 plus length of C plus length of D. With that, we've defined a length for any arbitrary concept in ALC. And it turns out that, as I mentioned before, we can indeed chop down portions, basically prune our search space, by simply predicting the length of the concept, which is of a concept which is likely to be a good solution to our problem. So basically, we can say this guy is, for example, way too long if you think about this particular search space. So do not explore here any further. Look at another example, even if our Q function says this is the guy to follow, right? And the way it's done is pretty straightforward, really. Again, it's via embedding, so we can embed the positive and negative examples and simply train a deep neural network to return an approximation of the concept length, which is to be expected based on these positive and negative examples. And we can then change the learning problem as follows. We can take our positive and negative examples, embed them, train a DNN, or use our trained DNN really to predict the concept length and use that really as a pruning mechanism for a refinement operator which is given to us. And well, a lot of different architectures have been trained here or tried. It turns out that a simple GRUs actually do the trick really well for all intents and purposes. This is not that important. What's important is more of this. So as you can see, basically, the architectures are not super different, but GRUs tend to have a more consistent output with respect to their prediction performance. And CLIP was compared to what's available out there with respect to class expression learning. And it turns out that is not only more time efficient, to our very surprise, it also tends to return even better F measures than what's available out there. So it's efficient and basically accurate with respect to the class expression learning problem. Major issue with this algorithm, obviously, is you have a deep neural network in there, and we're not completely sure as to why it's so good. We assume that it has to do with the fact that the data is clustered well in space, so if you have good embeddings, then you get a good predictor. Really, all the algorithm most likely does is sample in the space and say, am I in areas of high density? If I'm in high density areas, then basically the concept length, which I should predict, should be small, whilst if I sample from a lot of high density areas which are not connected, then I'm probably going to have a bunch of disjunctions, so I'm going to have a longer concept. But as I said, it's not 100% sure that that's how it works. That's still being explored. But to sum up, fundamentally, what I wanted to pass on as a message is, number one, we can make class expression learning viable, and we are basically going to need that if you have explicit representations of the world and we want to explain why, as a robot, we take a certain action. I wanted to show you that, yeah, changing representation seems to be rather important in this area, and that it really helps us to making the whole thing scalable, which has been one of the major reasons why class expression learning has been used only in a few practical applications over the last decades. But now that there are methods to make them more efficient, really they are being used ever more. We have a bunch of industrial applications now for class expression learning. But I also wanted to point out that fundamentally, so far we have guessed the correct representation based on our simply on our background knowledge. And one thing that I think is going to be a holy grail in future research is actually thinking about what is a representation and how can we select a representation for a particular problem automatically to actually make it perform efficiently or make our algorithms perform efficiently. That's basically what we're going to be dealing with in 2 research projects, which will start October 1st and January 1st. So you're more than invited to join us on that journey. Thank you very much. And of course, this is joint work with a lot of people who have done most of the implementation, evaluation, and so on and so forth. I'm open for questions. Thank you very much for listening. Ooh. I think the first question was here.
Yeah, can you hear me? Or Arthur?
I think
Arthur was first.
Yeah.
It's really quick. Can I have your slides, please?
Yes, sure.
Cool, thanks.
Can I have your slides too?
Yes, sure.
Yeah, so thank you also for the great talk. I have a question. So you already use neural networks to simplify several of the sub-problems that you're trying to address, right? So generating embeddings, approximating quality functions, predicting concept lengths, etc. So what do you think the chances are that the overall problem of class expression learning could one day be solved by, say, a generative model that takes maybe some observations about the world and generates class expressions that explain them?
So we just submitted a paper on exactly that. So the question was, do we actually need all of that machinery? Shouldn't we just be doing neural networks? It turns out that they work okay for simple problems, but then when it comes to rather complex problems, so if you take the data set hepatitis, for example, where you have really long class expressions and where changing a not to, or basically not having a not somewhere, basically messes up your quality completely, the devil is in the details there. They tend to perform rather poorly. I'm not saying that it's not going to be possible, but what we want to maintain is a certain amount of explainability. So basically, within the process, we want to keep the D and N part to a minimum, simply because, and as I mentioned on the first slide, we want humans to be able to understand why the robot does a certain thing at a certain moment. So it's probably possible to do that for a lot of data sets, but it's not necessarily what we would want to have unless we can explain neural networks really, really well. I think the next, I think the next question is over there.
Okay, here, the next one.
Yeah, thanks for the nice talk. In 1998, there was work on an algorithm called multi-relational decision tree induction. And that was pretty similar to what you did. And they made it on the basis of SQL and induced formulas in SQL. And they had a problem that in very, very many relational settings, the existence of some role is not sufficient and therefore will not ever be selected because it does not add any information in the Gini impurity, for example. How do you tackle that? For example, you showed that in slide 41, I think, that a role was selected with the fact top assigned to it. But yeah, that one in the left tree has role sibling top. I assume there are many problems where this is true for every instance, that it has a role to something, and this role has its name. Like, for example, in the mutagenesis example, you have atoms, and you have molecules, and every molecule has a bond. So your algorithm will never, ever select the existence of a bond.
Actually, it will, because we have type bonds. That's why it becomes rather interesting. So it happens, if you look at the solutions, even on the Siloe paper by Lehman et al., they actually have a bunch of solutions. And the existence of type bonds is actually quite central to mutagenesis. That's actually one of the reasons why the algorithm performed so well. Because the mere existence of a bond, I agree with you, not particularly exciting. The existence of a particular type of bond, particularly exciting, especially after that, because you have the class expressions here can be obviously longer. So you can have a type bond to, for example, arsenic, which in a lot of cases when it comes to discovering poisonous substances, it's quite prototypical. So yes, you are completely correct. There were works on using SQL, for example. That is still going on. MindsDB does a lot of work in that direction. But basically, we have different types of expressiveness here. And because we are dealing with Sparkle, or basically in this case, we're dealing with ALC, but when we also learn, for example, Sparkle queries. And if you think about Sparkle 1.1, where you have clean operators and the like, you're basically not dealing with the same languages. Hence, you also have different solutions.
Oh, okay, good. I see. Thanks.
Sure.
Okay, so thanks a lot for the nice talk. So if you want to learn concept, right, and basically apparatus of concepts, we want actually models that explain the world, that are compact with respect to each other, right? So in a way, I think the concept if we look at the physical domain, we would, for instance, like to learn the concepts that are underneath causality, right? So these are kind of dimensions that are just different, right?
Mm-hmm.
And so if we want to do that, so how can we do that? And
I'm not sure I understand the specification of the question.
so I mean, it's cool if you kind of if you get your knowledge graphs in and your kind of system makes up concepts that are cool, right? So and you're giving positive and negative examples for the concept, and it comes up with definitions of concepts that are more or less reasonable, right?
Mm-hmm.
But if we want to mine the knowledge graph, we would actually want, I think, a theory that explains what the knowledge graph represents, right?
Mm-hmm.
And that is kind of a step beyond that thing, right? And the question is,
how do we do that?
yeah.
Okay, cool.
What are connections there?
So there have been some works on ontology engineering based on class expression learning, and the fundamental idea there was, all right, if I have a particular knowledge graph which represents really a conceptualization of a particular domain of interest, I can ask the question, how is it related to other knowledge graphs, and can I explain this knowledge graph based on other knowledge graphs? These other knowledge graphs could be foundational ontologies, for example. And then I basically start saying, okay, imagine that I have a class and I take all the instances of that particular class as my positive examples, things that are not instances of that class as my negative examples. Can I explain this class with respect to a foundational theory? And again, then an explanation of the representation that I have of the world with respect to that foundational theory. And that's really how, that would be, from my perspective, a rather straightforward step towards explaining how I came about with my particular model. There are also explorative solutions where one basically says, well, it turns out that, and that's really statistical models, if you think about text mining, and you say, well, a particular subset of the instances tends to appear in particular types of tests, or if you're thinking about domain-specific crawling, for example, if I crawl the web in a focused way with respect to a particular domain, I only find a subset of the instances of my classes in there, especially if my classes are rather generic. I may say, these are positive examples, the rest are negative examples. Teach me what this really is, and learn class expressions for that. So it really depends on the use case, but in general, because we have, we have plenty of work on data integration, because we can take one knowledge graph and express it in a different knowledge graph, we have ways to actually explain the one theory in the other theory. And I think that's the key here.
Just one more question.
Yes, sure.
So you're basing the framework on a set of atomic concepts, right? And
Yes.
you assume that this is just a set. And but in reality, there might be subsumption relations already between the atomic concepts,
Yeah,
right?
that's no
So
problem.
like WordNet or some might. So how, and that would actually also influence class definitions, right? And
Correct.
so how is that?
We take that, we obviously take that into consideration. If you think about with the refinement operators, if you think about the refinement operator which is used, it obviously tries to exploit these relations as well, even if the classes are in NC. So let me just get to the example here. For example, if you think about refining a certain concept, we can obviously refine with respect to it. By exploiting subsumption, refine with respect to the subsumed concepts to have a tighter definition of what we're dealing with.
didn't see that,
So yeah,
yeah.
we do exploit the semantics as much as possible.
Cool.
And this is really just a small example. The refinement operators are usually significantly longer than that and really try to exploit semantics to the utmost.
Hey, thank you. This was the last question
Thank you very much.
because we are already on the lunch. So thank
Yeah,
you very
sure.
much for